There, are you there? I don't know. Yes. I don't know. Okay. Any questions, comments before we get started? Yeah. It's on the hill there. So you should have gotten an email about it today, also just because we emailed the entire campus. So if you didn't get that, let me know. We're gonna have an open house at the observatory, start between 7:38. You show up and it's day. I won't be there. Because you can't see things in space when it's daytime. Harder to do that. So I'm gonna try and get up there between like 7 and 7:30. You're welcome to come up early, obviously. The sun is beautiful when it's setting. Bring a friend, whoever you want. Basically, this is an opportunity to just like observe. If you're not able to come to any of them, for example, you have a class on Thursday or you work Thursday nights, let me know ahead of time. We'll just schedule more during the rest of the semester so you can participate. If you absolutely hate the idea of going to the observatory, also let me know, and we'll just do something else for that portion of the credit of this class. Okay? Yeah.
I was just going to ask about because I was out of town.
Yeah, that's a good question. I mean, we will stay there as long as people are interested. I would say you need to look at like 2 or 3 things. So if you wanted to leave in 30 minutes, 40 minutes, you could do that. Yeah. Yeah. So you'll show up, you'll put your name down. And then basically for credit in this class, what we're going to do is we're going to have you sort of like write what you saw. We're going to use EV scopes, which are cameras. So you can download the photos to your phone, and then you can include those in the write-up. So that's easier than drawing. We used to like have students draw through the eyepiece. I think that's a little silly because I'll never be that good an artist. But I can just send you the photos, and then you can be like, oh, I saw X, Y, and Z. And you'll have those pictures. Okay. You'll also notice here, the reading is kind of going to get disconnected from the lecture. They're the same topic, but I didn't write the book. If I had wrote the book, I would do it slightly different. So you see it repeated here, and we're going to have this piece here. I'm really hoping that we get through a majority of the topics that we're interested in, specifically talking about the planetary processes. Then we're going to connect them to how they occur. And then I'm going to show you an example of why we need to like modify that thinking. So if this starts to slip, that's okay. Your homework will slip as well. I won't provide homework that is on a topic that you haven't gone over yet. So if you start looking at the homework and you're like, this is not stuff we've done yet, just let me know. I'm trying to stay on top of it. Sometimes I'm not good at that. Questions before we start? Okay. You don't have to go to the observatory. We have an open house for the observatory. And if you are interested in going, you will get, I think, 5% credit. So I think the total amount for going to the observatory is 10%. So that's a pretty easy 10% to just show up and have a good time. Let's see if this works. Okay. It's on the schedule, but I said sometime between 7:30 and 8. And if it's still sunny out, when you look around, you won't be able to see stars, and we can't see stars with a telescope either. Yeah.
Where do we submit like the little write-up after we
You just bring it to me. So you can either send it to me via Slack or email, or you can physically print it out. And we can talk about that more in detail. Okay, so the nice part about this class is that if I think of something, I can just go back and change the slides. So here on the left-hand side is Mount St. Helens, before and after eruption. And on the left-hand side, you can see, that's like a traditional mountaintop. There's snow on top of it, everything's peachy. On the right-hand side, it looks a little different. What are the major differences you see? What's that? Barely any trees or like no trees at all. That's weird. Yeah. It's like a crater, yeah. So in fact, this is why a lot of people used to confuse volcanoes and craters when looking at them on, say, the moon, for example. They're like, well, it looks like it just even a giant hole in the middle. And especially those eroded craters, ones that don't hold their shape very well, they're very easily confused with volcanoes. There are some hints here that it's a volcano. In particular, you see the flows moving away from it. And this one's really cool. So these are direct images. So this is about a 60-second time period. In the top left, this is 10 seconds afterwards, 42 seconds. The entire mountain begins to collapse. 52 seconds and 60 seconds. So if you're hanging out like here, that's a pretty bad day. Okay. You may have heard of Pompeii. Ever heard of Pompeii before? So in Pompeii, it's a city that they built a little too close to a volcano, and everyone was coated in what's called the pyroclastic flow, which is like very hot ash and dust coming out of the top of the volcano, and it embalmed basically the entire city and people. And so the same thing is true here. The reason that you don't see any trees there, they all got burned. Right? So this entire area, basically there's a huge eruption and it destroyed all of the wildlife. There are actually pictures in here from people, scientists who were studying it at the time. And amazingly enough, he had the foresight to realize he was going to die. And so he like covered his camera with his body, and those pictures have survived because of his sacrifice. So that's what it looks like. Pretty incredible that just like in 60 seconds, a mountain could disappear. Anytime that I do this class and I think of cool things, then I feel like stuff happens in real life. So this is a meteor in I think it's in Ireland. I forget exactly, Scotland or Ireland, one of these two. It's pretty cool. So this is the picture of it burning up in the atmosphere. This is like 2 days ago. Saw it on Twitter. I was like, oh, that's really fun. And then this is an example of it happening at Jupiter. This is a very fuzzy image of Jupiter, of course, but this is a little time series. You're going to see it repeat over and over. You see it smacking into Jupiter. So that's massive. Like that's huge. If that hit the earth, we have a really big day, really bad day. But the nice thing about this one, Jupiter is really big. And for reasons that we can talk about later, it actually helps to sort of shepherd material into it rather than to us. That's really convenient that we have him looking after.
Where does that develop?
Well, we don't know exactly, but it's some form of either asteroid or comet. Okay. And I also talked about the Hawaiian sea chain mountains, and I said most of it's underwater. So in fact, if you look back here, you'll see that all of these are connected via tectonics. So this is a volcano, but it's connected to the tectonic process because the plate is moving over basically a soft spot in the crust, and that's forming the Hawaiian Islands. So if we zoom in here, we see all of these little numbers. These are the ages in millions of years. So here's the, I don't know how to say that, I'm not gonna try, but it's very young, brand new, underneath the water. This is the youngest part of Hawaii, and they can tell this because they can look at the rocks, you can tell how old the rocks are. And as you go back, you see the numbers are increasing. Right, so these are the older ones, and they're eroding and they're falling into the water. And interestingly enough, most of the Hawaiian sea chain is under the water, and then it even goes upwards. Why the hell would it do that? Guesses are fine. It's not like a prize here. We have a hot spot down here. These are formed because this is moving over the hot spot like this. Why do they go in a different direction? Because the yeah, this is the movement of the plate. So this was the movement of the plate currently, and this was the original movement of the plate. And it changed. It bumped into something and it changed the direction of the plate. And you can see that in the geologic record. Not very crazy. Okay, you can see lots of really fun stuff. I don't know how many of you had friends in elementary school, but if you didn't and you spent most of your time, let's say, looking at like atlases and maps, you'll see really cool things. Like here is the Rocky Mountain National Park range, essentially. And you see this is Yellowstone up here. Yellowstone is really famous for having hot springs. Those are basically fueled by the magma that's sitting right underneath the surface. It's huge. This is the caldera here. People call it a supervolcano. That's a misnomer. This thing is a giant pile of lava. If it were to explode, everyone in America would die. And what you can see here is as you look backwards in time, it is also moving. So this picture here with this hot spot is creating islands. Here it's doing the opposite. It's melting the mountains into flatness. So this is all really fertile region for farming because it's brand new magmatic soil. And here at the very top, it's burning its way through the Rocky Mountains. So as this basically moves, the crust moves over the caldera, it just melts any mountain along the way. That's cool, isn't it? Okay. Marginally cool. Okay. And then this last part, if you just look at a picture of the ocean lithosphere, we talked about seafloor spreading. So this is the place where seafloor spreading is occurring. And you can kind of like, if you're a puzzler, can match them back in your mind. Like that piece there goes right into that piece there. And actually the very first evidence that this was happening was fossil evidence. So we would find coastal fossils here on the edge of South America and African fossils there. Same date, same species. And they're like, huh, that's weird. And it's because they actually were from the same piece, broken apart by seafloor spreading. This is a form of tectonics. Tectonics is this little ridge here. This is brand new crust. And up here in Iceland, Iceland is famous for volcanoes. This is happening because someone decided to live on the edge of this tectonic feature. You'll see other ones, right? I don't know who chose this region. That's us living on the edge of a tectonic feature. This one's okay though, because it's sliding past it, as opposed to this one, which is splitting apart in a brand new way. Iceland's really scary because as climate change accelerates, the amount of ice that is holding down the magma, which is underneath Iceland, is decreasing. And so magma is getting to the surface more. And in maybe like 1,000,000 years, Iceland will just be gone. Now that's an exaggeration, but this is a potential that could really happen. Okay. So these are the ways in which we can see all of these processing fitting into one another. If you just sit and you stare long enough at a map like this, you'll see, okay, there's the Himalayas, that's the Indian plate smashing into the Eurasian plate, like we talked about creating the mountains. On the right-hand side, this is the Nazca plate here, smashing into the South American plate and creating the Andes. So mountains are formed by flat plates smashing into one another. New ocean is created by them spreading apart. Okay. So now we've talked about almost all of them. We haven't talked about this one. This is erosion. Erosion is surface changes made by wind, water, or ice. I'm going to show you 4 examples here. Which of these objects all on Earth? What are these made by? Anyone have any guesses? One guess per person. Yeah. Where? Top left one here. Yeah, so that's the Grand Canyon. That's formed by water moving over rock for millions of years. Anything else? Yeah, sorry. Bottom left by wind. Yeah, that's correct. So these are sand dunes. They are created by wind, moving small rocks, grinding them up as they go. Yeah. Yeah, bottom line's also rotted, very good. So this is like a flooding episode, right? So this one is a gradual river cutting into the bedrock, and this one is erosion, washing away anything that was there. Flood. What's that top one? Is that the weird one? Has anyone been there? I don't know what that is, sorry. Move this. Yeah. Yes, it is ice. Okay, so it's water, ice, and wind. So you could get it that way, but you could also potentially look at this thing here. If there are any climbers in the audience, they'll recognize that as Half Dome. So this is Yellowstone, Yosemite. And what you're seeing here, this little ridge in the middle, is carved out by glaciers. So back when there was glaciers in California, specifically in this region, basically ice bore through the middle of a mountain in the same way that we saw before, that magma chamber just cutting through the Rocky Mountain. This is from the top. So as the ice slides down, just pushes the mountain out of the way. And that's why if you look here, you have this beautiful face. It's like a cut. And that's exactly what happened. It's perfectly cut by a glacier. Okay. So, oh, that was weird. Okay, so these are all the topics that I just talked about: Colorado River, glaciers in Yosemite Valley, wind tearing up sand dunes, and erosion. Okay. So erosion is the wearing down or building up. So for example, sand dunes are built by wind. Erosion can also be thought of as like the destroying, say on the sides of a river canyon, by wind, water, ice, and they're all a function of weather. So if you don't have any air, you probably won't have any wind. If you don't have any liquid water, you won't have any water. If you don't have any water ice, you won't have any glaciers, right? Does that make sense? Okay. An important aspect, and we'll come back to this later, is that you need rotation to really have good weather. And I want to draw a distinction. We're going to talk about atmospheres more in detail later in this course. But there's a difference between weather, which is what you experience on a day-to-day basis, and climate. Climate is what you experience year after year after year. So for example, something like a tornado is bad weather, not bad climate. Liquid water is really important, tends to be the dominant form of erosion. If you have wind, that's great, but it won't do anywhere as much damage as water will. So we saw that, what, 2 days, 3 days ago, people's basements got all flooded. It's not as bad as when just a little wind blows your front door down. Right? Okay. What is this? Yeah. This is sand dunes, very good. Anything else? What about, this is a similar sand dune. Anything else you see that's weird? Yeah, these weird little shadow things, right? They almost look like shadows. In fact, they're not shadows. When we talk about what they are in a few seconds. What planet is this on? Venus, okay, good guess. I like that. Anyone else? Yeah. Mercury? Anyone else? Mars. Okay, so we have some really good guesses. No one said Earth. Why do you not think it's Earth? Because I asked. It's a good point. Okay. So this is in fact not Mercury, because Mercury doesn't have an atmosphere. So Venus would be a very good choice because it has a very thick atmosphere. But in fact, Venus doesn't rotate. It rotates really, really slowly. In fact, its year is about the same length as its day. So that leaves us with Mars. And this is in fact Mars. And this is what's causing it. This is a dust devil. Okay. So Mars has little dust devils. They come along and they disturb. So these are sand dunes created by prevailing winds. And then these little dust devils come around and they sort of stir it up. That's why they look like little squiggly squiggles. Okay. Technical term. Okay. Here's another one. What planet is this? Yeah. Now it's Earth. Why do you think it's Earth? The sun?
No, this.
The sand. The sand. Yeah. Okay. Any other clues? What about the angle of the image? So I'm thinking like from someone who might be standing there, as opposed to like this one, taking them from above. Like a spacecraft might. Okay. So yes, okay, I tricked you that this is the Earth. The largest sand dunes on the Earth are shown here. Where are they located? What's that? Sahara. Very good guess. I'm a trickster. That's not correct. Yeah. Dubai. Very close. It's also deserty. Not correct. Nope, not correct. Not the largest desert, not the largest sand dunes in area, the tallest sand. Biggest sand. Most mass. Here's California. That would be fun, right? If we had everything, we had like Yosemite. Yeah. I don't know that one. I don't think so. I think it's the Rocky Mountains. What? Good reaction. Okay, so this is called Great Sand Dunes National Park. And you're absolutely correct that your reaction should be what? So let's think about this. You have Rocky Mountains. They go north to south. On the right-hand side, you have like Utah, Arizona, Nevada. They're all deserty. right? So what causes sand dunes? Sand dunes are caused by wind pushing sand. So as the wind pushes sand across the desert, keeps going, having a good old time until it lands right next to the base of the Rocky Mountains, and it can't go up anymore. So it just gets accumulated over millions of years. Okay. So this is interesting phenomenon. If you spend like 20-30 minutes on Google Maps, no, Google Earth, whatever it's called, you just stare at the US, all of the secrets of the geology will begin to become apparent to you. Because you'll see like a mountain, and you'll see sand dunes on the left of it. You're like, oh, that must mean wind blows from the left. You're right. Okay. Questions about this? So there's also water on Mars. You may have heard a lot of people talking about this. This is the evidence, and we'll talk about it more in detail. Up here on the left-hand side, these are called fluvial features. You don't have to memorize that. That just means it looks like there was a river there. And so you can tell this was a river because you see all these little features. They look like little fans. Fluvial means fan. Any idea which direction the water would run in this picture? This way or that? Top to bottom, bottom to top. Bottom to top like that? How do you think that is? Because it spreads out. Okay, so if we think about it in the context of, and this is maybe a trick, if we think about this in the context of the geology, of course, we know that water would flow from the highest point to the lowest point. But as it's going, it tends to meet up with its friends and make a stronger river, right? So if I go backwards here, sorry, this might be too far. There are comments. Okay, here, which direction is the water flowing? It's actually flowing this way, right? Because all of these pieces, once they find each other, now they have more momentum together and they can push stuff out of the way. As you get a stronger and stronger river, it tends not to break up into smaller pieces, it tends to accumulate. Okay. Okay. Hold on, one more second. I don't know why I was calling it that. Okay. And then up here on the right-hand side, you can also see that it sometimes brings sediment up here. And then these are really interesting. So this is like if we were to punch into the surface to crater, and then after the crater formed, you have some ridged wall, and you have water flowing over it. And so you can see which was the direction of the flow. Left to right or right to left? What's that? Left to right. Yeah, so you can kind of see that with your eye, just like if you were imagining a rock in water. And when you put a rock in water, the water tries to go around it, and it creates this little teardrop behind it. That's exactly what's happening. And so the water moved from left to right. You can see that it moved around this crater, and it collected material behind it. Here, they were so close together, they formed this cute little island. We also see evidence over here. You can see it in the geologic record. These are hydrated minerals. This fun one is called blueberry. This is formed by rocks when they're in the bottom of a river. They roll, they become smooth. If you've ever picked up rocks in a river, they're not all jaggedy like the ones on the edge. That's because they're tumbling for like thousands of years. And so we see these really cute blueberry rocks inside of one of the rocks, which tell us that there were ancient rivers there. And for the most part, we don't see any liquid water on the surface, with slight exceptions. Every year, someone says, oh, we found liquid water on the surface. And most of it has to have a very important caveat that it's briny, very, very high salt contents. It's the only way that you could get liquid water on the surface. And this is not appreciable. These are not rivers. So here on the right-hand side, this is a time series where this is the edge of an exposed cliff with a little bit of ice in it, salty ice, and as it melts, it runs down. Okay. Erosion's quick, so pretty intuitive for folks who have been in rivers or seen here, right? Questions about these processes? Okay, so now we have to think about why did they happen. So in order to think about why they happen, we have to agree on some terms. So first, let's define some things. Like if we want to talk about different parts of the planet, we're going to define them by composition, for example. So this is the part that we live on. That's the crust. And below that, that's the mantle. And in the middle, there's metals. The core is mostly made of nickel and iron. The mantle is made of what we call medium density rocks called silicates. You don't have to memorize what a silicate is, I promise you. But they have silicon in them, silicas. And at the very top is low density rocks like granite and basalt. That might be counterintuitive to you. Like, what do you mean low density rocks? These are rocks, right? But the density, for example, of granite and basalt is something like 2 grams per cubic centimeter, compared to iron, which is like 5 grams per cubic centimeter. Okay. And if instead we define it by strength, the word lithosphere is a word that's thrown around. It means stone. Litho means stone. It means sphere. That's the outer layer of cool, rigid rock. The exterior is cold, and as we go in, it gets hotter, and the pressures go up. Okay.
Going towards the core.
Yeah, as you move towards the core from the exterior. So the exterior, the rock that we are standing on, is the coldest rock that you'll find on the earth. To go down into the surface, pressures go up, temperatures go up, and of course, rocks begin to melt. Okay.
That's why they're.
Yeah, and that's from the magma right underneath the product. Okay. So how do we know about the inside of the planets? Right, let's just look. So instead, let's think about this question here. The moon has an average density of 3.3 grams per cubic centimeter. Based on this density, you must conclude that it's either, here's your densities up here. Water ice is about 0.94 grams per cubic centimeter. Liquid water is exactly 1. Rock is between 2.7 and 3.7. And iron is 7.9. So is it all rock? Is it mostly rock with some iron? Mostly rock with some water? A mixture of rock, water, and iron? Or you can't tell, it could be any. Share your fist when you're ready. Okay, 3, 2, 1. Okay, all right. Most of the people are saying 1 and 2. I think that's about right. You might be tapping into some knowledge, for example, that it wouldn't be water ice. That doesn't make any sense. How are these concepts? How are we putting these concepts together? Does someone want to explain their answer, or do you want to? Yeah.
I chose all around because you can see that the density goes from 0.7 to 2.7. And you can see that when average density is 2.3. So it should probably be this density.
Yeah, so that would make sense, right? This number is right in between these numbers.
Iron.
So the reason that we think about all rock would fit perfectly between these numbers But of course, there's a little trick. You guys thinking about this?
Iron has some.
First, iron is heavier, but water is less heavy. So if I add the iron to the liquid water, and then I take the average of them, that's about 4. So here's 8 plus 1, that's 9 divided by 2, is about 4.5. So I could maybe weight that differently. I could say, well, let's say I had like 75% ice and 25% iron. You could get close to this, but we know that that's not what the moon looks like because you see it and it looks like rock, right? But this type of argument is something that we can use in order to assume what the general properties of the planet are. So we can put boundaries on it, right? That seems very unrealistic that 75% of the planet would be ice and 25% of it would be iron. That's not like any planet that we've seen before. So we could say, yes, I think somewhere between all rock and mostly rock with some iron would be good, right? There might be ice, there might be water. That's what people want to land there for in order to continue exploring into space, but it's a very, 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 very small fraction. Okay. We can tell the interior of the Earth super well. Better than this little weird table. Anyone know how? We actually use earthquakes. What happens is we have little stations set up all over the world, and they have very sensitive machines. Those sensitive machines can tell when there's vibrations. And so let's say there's an earthquake, say in Jakarta. That earthquake is going to propagate through the entire planet. It's going to propagate along the surface of the crust. It's going to propagate through the mantle. It's going to propagate all the way down to the core, maybe bounce off the core or bend through the core. And sure enough, if I have another station up here in Alaska, and let's say I have another one down here in Chile, the difference in the times that all of these waves get to us will tell us how it moved through the core. So for example, if it was the same material all the way through, then someone who was right here would get it at the same time as someone who's right here, as long as you account for the difference in the distance, right? And in fact, we can see that, okay, you have waves that glance off. All of these carry different signatures as they bounce in the interior. And then you have very smart people, not me, geochemists, who come along and they reconstruct that data using big models. Okay. So another way we can tell what the interior looks like, and we'll talk about this when we talk about moons in a little while. There's magnetic fields. You might have known this about the Earth, maybe not. If you go to the North Pole, basically where the planet is rotating, there's large magnetic fields that stick out of the Earth and come back down. This tells us how to get around with one of those old-fashioned compasses. And it requires 3 things. Okay, so the first thing it requires is that the body is electrically conducting. This means that it's metal. Okay, so just in the same way that like copper conducts electricity, the interior of the Earth conducts electricity. Okay, you also need convection. This is the same thing that we talked about earlier when we have heat that is being transported up, and then it cools and it comes back down. That's convection, right? And you need rotation. How much rotation is a subject of a lot of debate. Some people say Venus can do it. Some people say no. They're fighting in the papers. It's pretty funny to watch. Okay. So these are the ways that we can tell what the interior looks like. Now, you might say to yourself, well, how do we know what the moon is really like? Are there planet quakes? This is one of the places we've been to. The moon. Put a little seismometer down. Yeah, we said it was geologically dead. No earthquakes. Okay. So if I put a little seismometer down, I can tell that it's dead Because anytime that it gets hit with an impact crater, the whole thing is going to shake as though there was an earthquake. And we can tell the entire core is hard. Okay. We also look and we see no lava or anything else. There's no magnetic field on the moon, nothing like that. Okay. You can do this on Mars. Mars has a very, very weak magnetic field, but it's only in the southern hemisphere for weird reasons that we won't talk about. We recently flew a seismometer to Mars. We had it sit on the surface. Do you think we saw any earthquakes? Mars quakes, sorry. No, unfortunately, Mars is very close to dead. Okay. How does a world end up separated into these parts? Core, mantle, and crust.
Would be because, it cools.
It cools, yeah. So the exterior cools, that forms that nice crust. Why? Why? How does stuff get to the core?
Oh, the heavy stuff.
Yeah.
Isn't it from the rotation or mass comes together?
Okay, good. So I like this idea of like using the conservation part. We're going to use that when we talk about heating forces, but this one is just one step before that. Bob. It's called differentiation. Just heavy stuff sinks to the middle and less heavy stuff sits on top. So gravity here is pulling stuff towards the middle. All of this is being pulled towards the middle, of course, but the heaviest stuff falls towards the center. And the lighter material rises to the top. And it ends up being separated by density. So you might have seen an example of this, like if you are driving right after it rains, for example, there is usually oil on the road from everyone's cars, and then it rains, and there's a layer of water, and the oil rises above the water, and then you hit it going 65 and your car goes flying. Okay, that's a form of differentiation in everyday life. Here's another form of differentiation in everyday life. And you can make these really fun shots. If you're on the bottom, you have your heaviest liqueur, and then you have something in the middle like vodka, and you have like a cream-based liqueur, and they would just sit one on top of the other. So you might have seen like the child's version of this where you would put like a grape into say oil, and you would see them separated, like a washer would float all the way to the bottom. We can talk about why exactly this happens in liquids when we get to atmospheres. But the important part is that materials with different densities will totally separate from one another, given enough time. Okay, so if you've ever made salad and you have your oil and your vinegar, you put them together into a little like glass beacon, and then you forget that you made food because you did something really fun. You come back and they're separated. What the hell? Right? They separate because gravity is pulling the heavier stuff in. Okay. So what parts of the earth are liquid? Now this one's going to require that you've potentially already read through the book. So if you don't have an intuitive sense of this, you don't have to answer this one. Is it everything under the crust? Is it part of the core and part of the mantle? Is it all of the core and part of the mantle? Is it just the core? Or is it just the mantle? Your fist in the regular zone. Okay, 3, 2, 1. This one might not have been one for everyone who knew. That's fine. Here's what the interior of the earth looks like. And here's the crust, the lithosphere, that hard rock that we were floating on over this magma ocean, more or less. But basically, you have crust, mantle, outer core, inner core. And it goes solid, solid, liquid, solid. Very confusing. Okay, the interior is the hottest. You might think to yourself, well, it's the hottest, then it should be liquid, but in fact, the pressures are so great that it keeps it in this really solid form. The top, we of course know is solid. We step on that every day. I had a professor in grad school who's like, define a rock. Any definition of a rock? Yeah, it can be hard. Good. Yeah, we gave all sorts of definitions. We talked about like minerals and like the interior of the structure. And he said, no, something you can stand on. Okay, because this is going to get us to a really weird point where we start to think about ices as rocks. The only difference being between ice and something we traditionally think of as like made of, say, olivine or basalt. How hot is it? Because if I heat a rock up enough, it becomes just like water. It flows. Now, not just like, but close enough, right? For the purposes of our demonstrations. So here, the major difference between what we're thinking about is the exterior is very cold. Rock is able to condense. It's able to be hard. And as we go in, the temperatures increase. It melts until it gets to liquid. And then it goes back to being solid because the pressures are simply too large. Okay. Okay. Questions about this profile here?
So it becomes liquid because they melt.
Yeah. So up here, this is like magma. It's a weird type of sort of solid lava. But then as you go in, it's fully liquid rock. Yeah. Yeah, sorry, this is supposed to be like outer core, inner mantle. I might have moved them. They're supposed to be right on that edge there. Oops, sorry. Okay. So this is sort of telling us a little bit about like the exterior, this cold crust of the earth. The interior is hot. Now we have to ask a very important question. How long does it take for an object to cool off? And in order to think about this, we have to think about two things simultaneously. One, how much heat does it hold? And then two, how quickly does it lose that heat? Okay, and if I add those two ideas in my mind, I can figure out how quickly something cools. So intuitively, you already know this. What is cooler as soon as you pull it out of the oven? So it's Thanksgiving, you celebrate the Turkey Day, you pull out some potatoes and some peas. Which do you have to wait longer for? Same amount? What's that? The potatoes you have to wait longer for. Okay, why is that? Yeah, it has something to do with size. Okay, so one of them is big, one of them is small. Let's sort of think how we get through this. So the heat content, how much heat, depends on the volume. So if I have a bigger object, I can put more heat into it. But how do I lose that heat? I can only lose that heat through the surface. So that depends on the surface area. So for example, if I have a sphere, right? If the heat's inside, I can't like magically transport it out. I can only make it go out of the top, right? So if I then think about those, I want to just take the heat content, divide it by the heat loss. Some fun math. Already talked about that. Okay, so it's going to go like this. The time to cool is the volume, V, divided by the surface area. Okay. So for this one here, as you increase the radius of the sphere, what goes up faster, the volume or the surface area? Is it A, the volume, B, the surface area, C, it depends on the starting and ending radius, is it D, they both go up by the same amount? You ready? If you have any questions, you can ask a question right now. Okay, let's vote on 3, 2, 1. Okay, I only have 4s and 1s. I have a 2? No, okay, I don't know. Does anyone want to defend their answer? Why don't we turn to someone who is next to you, ask them what their answer was. See if you can convince them of theirs. Yours, not of theirs.
So that means that surface area. Again, based on-
Let's see if we can do a revote. Can you convince your neighbor? Everyone has an answer now, right? Okay, let's vote on 3, 2, 1. Okay. Anyone want to defend their answer? Yeah.
I think A, volume.
Mhm.
I might be wrong, but I just think of it as like the surface area would be depending on the radius. So like the volume by itself, I think of it as like increasing like a balloon.
Mhm.
So it increases first inside before the surface area and the radius, becomes bigger, so.
Okay, I like this, a very intuitive example. You're right that it is the volume. But there's actually an equation you can use too. And it sort of fits this intuitive answer that we have. So how does the volume depend on the radius? Does anyone know?
Yeah, the radius, as the radius gets bigger, then, the volume is bigger.
Yes, there's an equation. Does anyone know the equation for the volume, say, of a sphere? And maybe this is not common knowledge.
Oh,
I thought this was common knowledge, so this would make this problem a lot harder.
3.5.
3/4 pi r squared, pi r cubed. So in fact, hold on, where'd it go? It's literally written there in white, so this is super helpful to everyone. Okay, my bad. This is math. I promise it's math, but it's math you can't see. Let's do it over here. There's chalk in this house. There we go. All right, so the volume of the sphere. So this is R. Can you see okay? Okay. So here, this is the radius. Okay, And the volume of the sphere is 4/3 pi r cubed. And the surface area of the sphere is 4 pi r squared. So they look very similar to you because they're related. And I'm not going to tell you why they're related if you don't like math. But the thing is this part here, r squared, is going up more slowly than r cubed is. So for example, if r goes from 1 to 2, r squared goes from 1 to 4, and r cubed goes from 1 to 8. So the volume is going up more dramatically than the surface area, right? Okay. So the way that I tried to express this is that the time to cool is the heat content divided by the heat loss. So the content is the volume, how much can I hold? That's getting big quickly. But the loss, the ability to lose it to the surface, is not going up as quickly. So in fact, the time to cool is going to be proportional to the size of the object. So when we talked about why a potato is easier, or you want to wait on the potato and eat the peas right away, because they're small, they cool off more quickly. Does that make sense? Now you can explain that at Thanksgiving dinner. No, that's the stupid thing to say. Okay, so this is a different question, though. Okay, the lithosphere, the thing that we're sitting on, the cold rock part. The cold rock, sorry, the outer cool hard layer of the planet. Which of the planets should have the thickest lithosphere? Thickest lithosphere. In terms of percentage of a planet's mantle and crust. Okay, so let's go back for a second here. Let's look at the picture. God, this is so far back. Damn it. Okay. So the lithosphere is this cold part out here. Okay. And we're going to assume, we're going to ask this question, what type of planet is going to have the thickest one? Okay. Okay. So is it A, a large planet? B, a small planet? C, the lithosphere should always be the same percentage of a planet's radius? Or D, the lithosphere thickness does not depend on size? When you're ready to vote, grab your kids. Let's vote in 3, 2, 1. Fours. Let's see, twos, a lot of twos. Interesting. Okay. Anyone want to defend their answer? Yeah.
I have a question. So if like a planet is dead, does that mean it doesn't have a mantle or core? The whole thing is just like the crust?
So the mantle and core, remember, were definitions that we talked about in terms of composition. So the mantle is silicate based, and the core is iron nickel. But we didn't talk about what type of matter they are, whether they're solid or liquid. So this part here, the lithosphere, is it's hard, non-liquid, right? So, good question. We're just using these terms for the first time. Basically, I'm asking, you think about the exterior of the planet, right? Which of them have the hardest or the thickest crusts? Anyone want to defend their answer? No? I have a lot of people picking 2. No one wants 2? So what is the heat loss depending on? Surface area. What is the content depending on? The volume. So the larger I am, the more heat I can contain. But the surface area here is not going up as quickly. So my ability to cool or my inability to cool gets worse as I get larger. So the potato is hotter. The interior, say of the pea, can cool out very quickly. Okay. So which of these do we want to defend here? Yeah.
So I think it would be B,
Uh-huh.
because since it's a small planet, then the volume would be less
Yes.
than a large planet, which means that the content affects them only. So because it's a small planet, it wouldn't have that much heat content compared to the large planet. So the cost would be because
Yeah, thicker overall. So if we go back. Oops, sure. The larger objects take longer to cool. Oh, this is the map that isn't showing up. Okay, so we can do that by just looking at the pictures. So here, in fact, this is the each of the different planets. And on the left-hand side, you have the Earth, best planet. Then you have Venus, second best planet, Mars, tied, I guess, whatever. Mercury and the Moon. And you'll see that the lithosphere here is shown by this little dashed line area. So for Earth and Venus, which are still very large, they have held on to all of their heat. The interior is still mostly liquid, right? Where there's a section of it that's mostly liquid. Whereas the lithosphere for Mars is quite thick. Because it's smaller, it didn't start with a lot of heat, and it was able to get rid of it in the same amount of time that we've been hanging out, right? Same thing's definitely true of Mercury, but something else very weird is happening there. And the Moon is almost all of the sphere except for the core, right? So the way to take this off is to think about that smaller worlds are cooling off faster, and the exterior is hardening. So as the exterior hardens, if, for example, you had volcanism is when magma from under here is able to get through the lithosphere. If the lithosphere is really large, are you going to have volcanoes? No, because magma can't seep through the surface, right? Similarly, if you hit it like an impact crater, smash into it, and there's just like lithosphere all the way down, you're not going to get any of those lunar maria that you used to get. You don't have any floodplains of lava anymore, right? So once you get a lithosphere that's going really deep down into the planet towards the core, then you don't have any geologic activity. Okay. Questions about this? Okay, so we're already seeing how size is important. Basically, planets are going to have 3 fundamental properties when we talk about them. We talked about size, which includes mass and radius, sort of put together. We're going to have distance from the sun, okay, how far away they are, and rotation, how quickly they spin. And we'll talk about these all in detail. But you should be able to rank the planets in these categories. So just for the terrestrial planets, which terrestrial planet is the closest to the sun? What was that? Mercury. Which terrestrial planet is the largest in mass and radius? Earth. Very good. Which terrestrial planet is the smallest in mass and radius? The Moon. I would accept the Moon. Mercury is also an acceptable answer. Both of those surfaces, remember, looked really similar. In fact, if we go back one, their sizes are fairly similar. Now, something really weird is happening at Mercury, but we'll have to talk about that another time. Okay, so before we. Yeah, I think we have time for this. I think we can talk about comparative planetary geology at this point. I'm gonna pass some of these back. Yeah. Passing them on. We can at least get started on these. And I think we'll be able to start putting these different effects into context with one another. In particular, I want to draw on this idea that if I tell you the size of a body, the distance it is away from the sun, and the rotation rate, you can tell me what geologic processes are going on the surface. Okay? This, I guarantee you, will be on the exam. I will ask a question, and the question will be straightforward. Okay? It'll say, based on these three properties, describe whether or not this is present or absent. And the reason that I give you these little lecture tutorials and have you fill them out is I want to see your own words. So saying something like a one-word short answer, you're already not doing it because I read all of them. But like go through the process of explaining yourself, because that is exactly what I'm willing to give plenty of points for, to see that thought process, right? So this is all practice for the exam. The exam will probably be take home. I know you're really excited about. And will allow you to use a computer and calculator and reference the book, because it will require exactly what you're doing now, which is thinking and describing your thinking. I found that it's really hard to cheat that way. It's really easy if you just say like 4 times, everyone can write 4 times. But if you say, well, why is this hot? You have to write some words, and you can see the first, right? Okay. Okay, so let's try and do this in like 10 minutes. If that's not possible, obviously you take them home, you bring them back Tuesday, we'll try to do it Tuesday. Okay? And then that's it. No worries. I just wasn't sure. So I bring it home. Great. So remember that we're working. You two should be working together. What that? Yeah, even if you both have a paper. For example, your first instinct might go, bounce it off that line, because they might have a different. I know. Yeah. Yeah. Which one? Yeah. Yeah. Yeah, go through that, so it still has real life activities, because the geologic activity is influences this event, and that's higher. How hard it's Mercury is a weird object. So if you put Mars and then Mercury, and we can so Mars is actually sort of yeah, so Mercury has a big core, but we'll talk about what happened to its sphere. Essentially something really bad happened. It used to be a massive planet, but now it's not. Yes, Mars, Mercury. So they're in the right. But if you switch these, I would not.
Yeah, I mean. I believe that the mark will be the next. But again, the mark till it's done. But there's not much. I just said that. Wait.
Okay, folks, technically, I think we're out of time. You're welcome to, I'm not gonna force you to leave. I don't think anyone's for us. If you want to finish, you're welcome to finish. Otherwise, I will see you either tonight or on Tuesday. Yes. Yes. Yeah. Oh, thank you. Oh, this is not.
No.
Okay.